Okay. Recording, yes. All right, this is Physics 1C for March 23rd. Today what we're going to be doing is talking about electric current. We'll understand what that is, and we'll talk about current density. We're also going to talk about resistance, and then we'll talk about electromotive force and electrical power. So this chapter is really all about introducing really just new terms, I guess. Probably terms that you've heard before. You've probably heard the term electric current. You've probably heard of the term resistance. I've talked about it in this class if you hadn't heard about it before today. So this chapter is really just about defining what those terms mean and how we calculate them and what is current, what is electric current. And then in the next chapter we'll look at some kind of applications of how we apply these ideas to electric circuits. So that is the plan of action for the next couple weeks. Both of these chapters are pretty straightforward. So if you don't understand anything, please ask, because most of the stuff is, like I say, it's really just about introducing concepts. Most of them are pretty straightforward. All right, so the first thing we want to talk about is electric current. So in order to understand what electric current is, we're going to think about the places where we find it. So suppose that I've got a wire that's a conductor. So this is a conducting wire. Now, of course, most wires aren't this thick, so the idea is we're kind of zooming in on this wire right here. Now, what is it about conductors that makes them different from insulators?
Charges can flow freely through them.
That's right. So there are free electrons inside of conducting metals that are free to effectively flow almost like a fluid, okay? So within this conducting wire, you've got little tiny electrons, which I'm going to draw a little bit bigger here. And yeah, in general, they're basically free to move around as much as they want. It's not every single electron within the metal that's free to do this, though. Generally, what happens is that in conductors, the metal itself will have like one or two loosely bound electrons in its outermost shells. You all know about electron shells from chemistry, maybe? I don't know how many of you have taken chemistry. But the idea is that if you have an atom like copper, for example, what is copper? Is it like 22 on the periodic table or something like that? Anyone know? Normally, if we were teaching in a classroom, we'd have a periodic table just on the wall.
29.
29, okay. Let's just pull up the periodic table here. All right, where's copper? Copper, 29 right there. Okay. So what does that 29 represent for those people that maybe haven't taken chemistry? Although I bet a lot of you have taken chemistry. What does that 29 mean for copper? Oops. What does the 29 that sits above the name of copper represent on the periodic table?
The number of protons.
It's the number of protons. That's exactly right. And since atoms are neutral, it's also representative of what else?
The number of electrons.
Also electrons, right? Okay. So it's 29 protons. And as long as it's not an ion, it's also 29 electrons. That would be a copper atom, okay? Well, it turns out that when you start to stack this many electrons around the protons, I mean, how much detail do I want to go about this? I don't really know, like, what people know, so I should maybe do some things. So the way an atom works is you've got a nucleus that's extremely small. Very, very small, on the order of like 10,000 times as small as the atom itself. Bound with inside the nucleus is all the protons, along with a bunch of neutrons. I don't know how many neutrons there are in copper, but I will say that the number of neutrons that a copper atom has is dependent on which isotope you're talking about, and it's not really important for what we're going to discuss here. But then around this nucleus, you have shells of electrons, right? These electrons that are going in all sorts of just different paths, but you can imagine that there are just like different levels of electrons all surrounding this nucleus here, okay? And when you get to the outermost part of it, and this is the part where we can actually talk about electricity, is what we know about it, right? So imagine that every one of these rings has some number of electrons on it. Maybe there's 2 on the first ring, and I don't remember the numbers, but maybe there's 6 on the second ring, and whatever. You've got a bunch of rings of electrons, right? Once you get out to the very most outer shells out here, the electrons are extremely loosely bound because if you think about it, if you think about Gauss's law, right? Let's imagine that there are 29 protons in the center, down here, and then you have 28 electrons up to this outer shell right here, okay? And then this is, let's say, the 29th electron, right? If we used Gauss's law to analyze this system, what would the total charge enclosed by the orbit of this outer electron be? Does that question make sense? How much total charge would be enclosed by the outer orbit of this electron here? If you've got 29... Inside this outer shell, you've got 29 protons, and you got 28 electrons. How much total charge do you get if you add all that up?
Which is a positive 1.
You play out plus 1e, right? So think about that. That basically means that this outer electron is effectively shielded from the nucleus by 28 other electrons, to the point where it doesn't feel nearly as much of an attractive force to that nucleus. Like, the nucleus is positive, the electrons are negative, right? So then electrons are naturally attracted to the nucleus. But the outermost electron is very, very weakly bound. And within a conductor, that's what these electrons that I'm drawing here are. Just the weakly bound outermost electron. And it's so weakly bound that it doesn't really need to stick with its atom. It can basically flow freely throughout the conducting wire. So these are what we call the free electrons. And they're the things that are going to be responsible for the phenomenon that we call electric current. It's going to come from those free electrons. Okay. Now, it doesn't have to be copper. You can also have conducting wires that are made of silver or gold or all types of different metals, right? But very commonly, the wires that we use are copper. Okay, so how do we get a current? So an electric current is a type of flow of the charge through the wire. It's kind of similar to a current in a stream or a river. So electric current is the net flow of charges in one direction in a circuit. Now, if we have a conducting wire, and inside of this wire, if there's no electric fields, meaning within the wire itself there's no electric field at all, okay? No external field applied to it, then the charges are basically going to be free to just kind of move around randomly. Little tiny particles like this, they tend to kind of jiggle about. They don't really stay in place, okay? They tend to just zip around. In fact, the electrons themselves, these free electrons basically act kind of like molecules of a gas. And what gas molecules do is they just kind of zip all over the place. They have random velocities, they have random rotational motion, and all of that random motion we kind of interpret as the macroscopic phenomenon that we call temperature, okay? So when I say they act like molecules of a gas, that means that they zip around all over the place, they jiggle randomly, they rotate, they do all kinds of just random motions. They're also influenced by each other, right? So if we were to look at one of these electrons and what it does, it would basically tend to kind of just zip off in one direction until it hits something, and maybe it might rebound and reflect off this way, and maybe it get close to this electron and it rebounds and reflects off this way. And of course, there's other things inside of this conducting wire too. There's also nuclei that are kind of bound in place, and these charges are basically just kind of zipping and bouncing all over the place. Every single one of them is just randomly moving all throughout it, as long as there's no electric fields. Okay. Now, the moment that you do apply an electric field, and so this is what this picture down here is for. Why can't I expand it? That's weird. Oh, it's like... Look at that. It's like it's off-center somehow. It thinks that's the corner. Why would it be doing that?
That's weird.
I don't know. That's going to be kind of weird for today. I guess I'll just get used to it. So above is a conductor without an electric field, okay? And this little blue thing is a negative charge, okay? It's an electron. And this down here, this little box, zooms in on what that electron's doing, okay? So similar to what I'm saying up here, if we look at this blue line, there's two lines here, right? There's a blue line and there's a pink line. Hopefully you can distinguish between the two of them. I guess if you're colorblind, these two probably look pretty close. I don't know. Depends. Anyway, so there's two different paths here. The blue path is the path that the particle would take without an electric field, okay? And just consider this to be kind of a random path that this particle is taking, right? The places where it changes direction means it hits something, okay? Now, what it hits, it can either hit another electron, or it can come close to another electron that repels it back off this direction, or there could be a positively charged nucleus right here that it's basically like kind of slingshotting off of, okay? But nonetheless, that's what the random motion is going to look like, okay? Now, if we apply an electric field to this conductor, that's what this picture down here is. So we apply a electric field that points in this direction. And how would we do that? How would we get an electric field to be applied to this conducting wire? Any ideas how that might happen?
We could maybe hook it up to some source of potential.
Yeah, we just need to hook it up. Yeah, we need to hook it up to something that creates a potential difference between the ends, so that this point is a high potential difference, high electric potential, and this point over here is a low electric potential. And then you're going to get a net electric field that's going to point in that direction. And like you said, you do that by putting a battery in here. So we'll just drop a battery in here, put the positive side on this side, and the negative side on the other side. So this is the positive side of the battery, this is the negative side of the battery. It's going to have some potential difference, delta V. That's also going to get applied to the wire itself. So connecting a battery up to the wire is going to place an electric field inside the wire, and then the force placed on an electron is going to then be to the right, because electrons feel a force that's equal to Q times E. They have a negative charge, so the force is opposite the electric field. That means that there's a net force acting on all of the electrons within this wire that is going to tend to shift the electrons in the right direction, okay? Now, this doesn't mean that all of a sudden every single electron just starts moving to the right. That doesn't happen, because they still have their own momentum. They have their own inertia, right? So for example, if we think about what this particle is doing, look at this blue path right here. If we look at the blue path where it's moving to the left right here at the beginning, if there's an electric force acting on this particle, it's not just immediately going to start shifting to the right, right? And I'll give you an example of why that's true. If I take a ball and I just drop it near the surface of the Earth, it falls straight down, right? Because there's a gravitational field that points downwards, right? And that gravitational field tends to make the ball go down, right? But what happens to the ball if I throw it in this direction? It doesn't just immediately fall to the ground, right? It kind of goes like this. It goes along kind of a projectile type of path, right? So the particles don't just immediately start moving in the same direction as the electric field, but they feel a force in that direction, which means it's going to alter their motion, right? That's Newton's first law, right? The particle is going to keep moving in a straight line until it's affected by a force. Well, now there's a force, and its motion is going to be altered. But that doesn't mean they're going to start moving in a straight line in the path of the electric field. Instead, what's going to happen is they're just not going to move as far as they did before. So this pink line right here is supposed to represent what happens to the electron as a result of the electric field. And now what we do is we compare this final point P2, which is where the electron ended up with no electric field, and the point P2 prime, which is where the electron ended up with an electric field. And there is some distance that they travel right there. That distance, it's hard to see right there, is Vd, which is going to be what we call the drift velocity, times the time interval over which the particle's been moving, okay? So this term V sub d is what we call drift velocity. Because what's happening in this system is that these particles are drifting to the right, all right? And as they drift to the right, that's going to represent electric current, a net flow of charge in one direction in a circuit. All of the individual particles are still randomly bouncing around. It's just that over time, they're being kind of slowly shifted to the right, okay? This would be true of the molecules of a river, too, if you think about it. You think about a river, which is composed of water molecules along with whatever else is in there. And if there is a current in the river, the current is going to kind of tend to make all of the particles flow in one direction, right? But that doesn't mean if you look at a single individual molecule within the river, that molecule is automatically having to be moving to the right, right? Because molecules they observe like random motion, right? So even the molecules of a river, let me draw a picture so I'm not just, let's say you have a river, and let's say you have a current that's flowing in this direction. And then I go down here and I look at a single molecule of the river right here. You can't say for sure that molecule at a moment in time is guaranteed to be moving into the right. Would you all agree with that statement? it could be kind of moving off in this direction, but eventually it is going to be kind of carried back forwards. But then it might bounce off another molecule and get bounced back this way, right? So an individual molecule isn't necessarily going to be moving to the right. It's just that the ensemble of all the molecules over time is moving to the right. Does that distinction make sense to you all? Mm-hmm. Now, I don't know how important it is to understand this, but it is going to be important to understanding what this thing is. Because when we talk about drift velocity, what this is basically the kind of average rate at which the electrons are flowing. Average rate at which. Okay. Now, an individual electron is not going to have this speed. It's the average speed of the collection of all of the molecules, right? That's the idea of what it is. Okay, so to get electric current, you need two things. You need a wire, and you need a potential difference placed in the wire, which will then place an electric field there. That's all you need. You just need a battery and a wire, and you're going to get electric current flowing through the wire. Okay. Now, in order to define and understand what this is, since there's a net flow of charge in one direction, what we do is we define this thing that we call current. Okay, so if I have a wire, and I do exactly what we just said, so we take this wire and we attach it to a battery, like this, positive side here, negative side here, then we're going to say that it sets up a current flowing in that wire. It's going to flow from high potential, which is this side, to low potential, which is this side. And the symbol that we use for current is I. So I is the symbol we use for electric current. I used to remember why we use the symbol I, but I don't remember off the top of my head. So that's the symbol we use for electric current, and because it's related to a net flow of charge in one direction, we basically just say that we can define this as the rate at which charges are flowing, so we basically just define it like this. It is the time rate of change of charge flow within a circuit. So if you can count the number of charges, for example, that flow past some cross-sectional area here, and you say, I don't know, maybe 10 coulombs of charge pass by that point in 1 second, right? You take the ratio of the amount of charge that flows by. So if you have 10 coulombs that starts over here, and it crosses from here to here, and ends up on this side of that cross-section, and the time that it takes to go from that position to that position is about 1 second, then you can say that you have 10 coulombs per second of flow, which is going to be equal to 10, and then we use the symbol. Whoop, all this stuff is behind the thing, I'm sorry. How far over do I have to? I'll just scroll down a little bit. We'll just go right here. So if you have 10 coulombs that flow by in 1 second, then that's going to be equal to 10 ampere of current. 10 amps or 10 amperes of current. So the symbol we use for current is capital A, and that's how we measure it. We measure current in amps or amperes or A. And it's named after I want to say French scientist, I believe, Ampere, who we will talk about later on because we're gonna learn about one of Maxwell's equations comes from Ampere, called Ampere's law. All right, so that's how we measure current. We measure it in amps. And the next thing we'd like to do is to kind of quantify for an amp of current, for example, what does that mean in terms of how fast the charges are moving? So that's what we want to figure out, is how fast do these charges actually flow through the circuit here? If we say that there's 10 coulombs per second, what does that translate into in terms of the rate at which the charges flow, or what we call the drift velocity? That's kind of what we want to figure out. Maybe before we do that, I'm gonna show you this simulation that I pulled up here. Again, if you want to find these things, this is from, let's see if I can show you exactly where I found this one. This is from Phys website, and I had to, which one did I click on? I don't even see it here now. Oh, it's right here. Battery resistor circuit. This is the one. By default, it wasn't there though. This is what I got when I searched by default. It puts this HTML5 thing down. So if you turn on all these things, then you'll get the Java things too. It says that Java sins run on most computers. I don't know. But this is the simulation right here. This is a circuit that contains a battery and a resistor. You know what? This is actually a little bit ahead of what we're doing. Because we haven't talked about resistors yet, have we? Yeah, okay, we'll come back to this. And we'll actually try to look at it. I could show you what it looks like when we play this, though. So basically what we have is a... we've got a battery. We've got a circuit here. Okay. And there's a voltage right here, which we can manipulate. And then these little blue balls are electrons. And then this red thing is basically just a conductor. And the I can turn these little things off, but there's the electrons flowing through there. You kind of notice that the electrons are chugging along. When I click show cores, each of these green things right here is supposed to represent, I believe, it's supposed to represent a nucleus. And the nuclei, the idea is that they tend to kind of stay in place, but they can also jiggle a little bit, okay, as a result of these electrons flowing through here. So you can imagine that as these electrons flow through, and they don't flow straight through, they bounce around randomly as they move through here, but this is just a simulation. They interact with the material itself. They interact with the nuclei. And the effect of that is that it can affect the temperature here. This little wheel measures current in amps down here. If we increase the voltage, the current will go up. As you can see, the charges start to flow faster, and the reading right here gets higher. And you'll also notice the temperature increased up here. We're going to come back and look at this after we talk about resistance, though, now that I think about it. A little bit too soon. It is kind of a nice representation of what we're talking about, though. All right, so we want to, again, figure out this drift velocity thing. How big is the drift velocity? How fast are these charges actually moving? Are they moving like close to the speed of light? Are they moving really slowly? What is the drift velocity? That's basically what we want to figure out. So here's a couple of pictures from your textbook to think about this drift velocity. Let me make this a little bit bigger so we can actually read what's being written on there. Okay. So we want to know how fast the drift velocity is. So we're going to simplify our model of what's happening here. And while we know that the electrons tend to bounce around all over the place, we're going to kind of treat them as if they're all moving with their average speed with this thing called the drift velocity. All right? And so our picture of the circuit is going to look something like this. So in the top picture right here, we have what's called conventional current. All right? And it's treated as the flow of positive charges regardless of whether the free charges in the conductor are positive, negative, or both. So it is possible that the conductor could have the free charges be positive. Usually the free charges are negative, okay? So as it says in the bottom, in a metallic conductor, the moving charges are electrons, but the current still points in the direction that positive charges would flow, okay? So electrons are going to tend to move to the left, but we still define the current flow to be to the right, even though the electrons are going backwards because they're negative, right? We're interested in the direction of positive charge flow. So what we're going to do to kind of simplify the calculations that we want to do is we're just going to act as if the charges that are flowing in the circuit are positive, just so we don't have to worry about negative signs showing up on our equations. So we're going to kind of treat this as if it's our model of what's happening. So we imagine that our conductor has a bunch of free positive charges that all flow with a drift velocity that we call v sub d. It's really equivalent to talking about negative charges that are moving to the left if we have positive charges that are moving to the right when we discuss current. But current is the direction of positive charge flow. That's how we've defined it. I think, and maybe I'm wrong about this, but from what I've heard from engineers, I think that sometimes they actually define the direction of negative charge flow to be positive. I could be wrong about that, though. I've just heard that. It's not something, like, I didn't take any engineering classes. But in physics, we always use the positive direction. So, and I think usually in engineering, maybe they do too. Maybe it's just certain scenarios where you do the negative charge flow. All right, so now we have another picture here. This is the picture that we're going to use to try to figure out how fast the drift velocity is. So we have a circuit here. There is a battery, and there's a wire represented by this black line. There's also a light bulb that's lit up here. And we have a cross-section of the wire that's been blown up right here in this picture. And we have all of our little charges that are flowing. There's a current that's defined as the rate at which the charges flow, dq dt. And then we have this cross-sectional area here. And we're really going to kind of investigate what's happening at this cross-sectional, across this little area cross-section here, right? So through the cross-section A, charges flow. And what we'd like to do is we'd like to calculate how much charge flows. And then we're going to kind of divide that by the time to figure out the current and relate it to the drift velocity. That's what we want to do. We want to calculate how much charge flows across A in a time dt. Okay? We're going to define the amount of charge that flows through as big dq. All right? And we're going to say, what is this going to depend upon? Well, the thing that it's going to depend upon are going to be how much charge is actually on one of these charge carriers, which we're going to call Q. That's going to be the charge on a single charge carrier. We're also going to want to know how many of these charges there are per unit volume, which we're going to call little n. This is going to be the number of charges per unit volume. And I think that's it. That's all we really need. Okay, so if I want to know how many charges flow from the left side of this to the right side of this, I can say that if I take the charge on a single carrier and I multiply by the number of charges per unit volume, and then I multiply by, what would I need to multiply this by to figure out how many charges are actually in this regime right here?
The actual volume in that.
Yeah, just multiply by the volume. And what would the volume of such a regime be right here?
Just the cross-sectional area times the drift velocity times dt.
Yeah, so basically it's going to be A multiplied by the drift velocity times this time interval, basically. And why do we multiply by this? Well, this gives us a distance, right? This would represent, what does VDT represent? I should actually write that over here. What does VD times dt represent? Now remember, our goal was to find how much charge flows through A in a time dt, right? So what would VA times dt represent?
Can we call it the drift distance or drift length?
Yeah, but can you say more? I mean, I agree that's a good thing to name it, but can you say more about what does that mean?
Basically, like the whole ensemble on average moves that distance.
Yep.
in that time.
Exactly. And we could even apply that to a single particle, right? We could say it's the distance traveled by really any charge in time. I'm sure I'm okay. In time dt. That represents, for any given particle, because remember, we're simplifying our whole circuit, and we're treating it as if all of these particles they're all flowing with this constant speed, right? And if I have a bunch of particles, they're all flowing at a constant speed, and I want to know how far they go in a small interval of time, then you can just say, well, it's just the drift velocity, that's their rate, times the time that you're talking about, right? Okay, so Going back to what we were doing, we said that we could find the amount of charge that crosses that area by taking the charge on a single carrier. We multiply by the number of charges per unit volume, and then we have to multiply by the volume, which you said was the area multiplied by the distance, which is v dt. Ugh, looks really bad. Drift velocity multiplied by dt. And all of that is basically this is just volume, right? And this is number per volume. Is that enough? Is that it? I think that's it, right?
Mm-hmm.
That should be the amount of charges. That right there should be the total amount of charges. Okay. Now our goal is to find drift velocity, and what we're really going to do is we're ultimately going to solve for drift velocity here. But what we need current. All right. So what we're going to do is we're going to divide both sides of this equation by dt. So we'll divide this side by dt. We'll divide this side by dt. What that'll do is it'll cancel out this one. The left-hand side now is going to be what our definition of current was. If I scroll up a little bit, you can still see it. That the current was defined as the time rate of change of charge flow. So if I know the amount of charges that flow through that regime, and I also know the time that it takes them to flow through, then I basically now just have current, right? So the left-hand side of my equation is going to say that the current flowing in my circuit is going to be equal to the charge on a single carrier. This is almost certainly going to be the electron charge, basically. Since a single carrier in this case is going to carry the amount of charge that an electron has. We multiply that by number of charges per unit volume. You multiply by the cross-sectional area of your wire. And then you multiply by the drift velocity. And that gives you the current that's flowing in the circuit. Let's see if this makes any sense. So the first three terms right here basically just define kind of the quantity of charge that you have that's flowing. And the last term tells you the rate at which that quantity of charge is moving. And when you combine all that stuff together, which is the total amount of charge multiplied by the rate at which it's moving, that gives you the current. Okay? And if you think about it, it helps you to understand why current is very similar to velocity. It's basically just like velocity multiplied by charge, if you think about it, right? That's really all it is. It's just telling you, the current tells you really just how fast the charges are moving. If I increase the current over here, but I keep everything else the same, meaning this doesn't change anyway, the number of charges per unit volume is dependent on the type of material, and the cross-sectional area would just be the area of the wire. So what happens to the drift velocity if I increased the current?
It must increase.
It has to increase. So it's a really simple, it's a direct relationship, right? If I go from 2 amps to 8 amps, and I quadruple my current, the drift velocity should also quadruple, right? If I triple the current, the drift velocity should increase by a factor of 3. If I cut the current in half, the drift velocity is going to decrease by a factor of 2. So it's a really nice direct relationship. All of the things right here depend on the type of material, and that's it. They depend on the type of the material, and they also depend on how thick your wire is, right? So what happens to the drift velocity if the area of the wire goes up, but the current stays the same? So we make it has to go down, right? So if we keep the same level of current, but we use a fatter wire, right, like double the size of the wire, the drift velocity has to decrease. All right. What happens to the drift velocity if we make the wire half as big? We cut the wire in half. So instead of having a wire like this, maybe what our wire does is it's like a hose, maybe, where it kind of it gets smaller in this regime right here, and it decreases to a factor of A/2. What's going to happen to the flow of charges in this regime compared to this regime over here on the left?
Twice as fast.
They move twice as fast, right? Does that look like anything you've seen before?
Looks like Bernoulli's.
Yeah, I was gonna say.
Yeah, it's just like Bernoulli's equation, but for those people that maybe haven't taken 1B, what does that look like to you? So I tell you I've got this object that has charges flowing through it, and then I tell you that the charges get faster whenever the size of the wire gets smaller. What does that remind you of?
Oh, it's like when you're telling us like how when we get shocked, it's usually on the tip of our finger because that's like the smallest area, right? So it's like the greatest.
That's not what I'm thinking about in this case.
I was thinking about like a water hose.
Water hose, yeah. You guys have all taken a water hose and put like a nozzle on the end of it, probably.
Yeah, if you pinch it, it
Or if
comes
you,
out faster.
if you just pinch it, right? If you just put your thumb over it, or if you have a faucet, like your sink in your house, and you put your thumb over the end of the faucet, the water will come out faster, right? So it's exactly the same concept. When the cross-sectional area gets smaller, the charges start to flow faster, basically. All right? Okay. So that is our relationship for current to drift velocity. But now what we want to do is we want to start talking about some new concepts. Now we're going to calculate drift velocity in a problem that we're going to do here in a second by using this equation. Okay, so I'll just kind of box this equation here. All right. Remember what these things represent. Now the next thing we want to do is we want to take the area here and we want to divide it underneath here. And we want to define something new. So we're going to define something that's called current density. Okay. And current density is basically going to be equal to, we use the symbol J for it, and we define it as being equal to the current divided by the area of the wire. And this is going to be equal to, well, you can see right here, it's just equal to Q times N, the number of charges per unit volume, multiplied by the drift velocity. So that is what we call current density. It is the current per unit area. And current density is actually a vector, okay? So current is a scalar. It can be positive or negative, but it's just a scalar, okay? Current density is a vector. And the direction of the current density is actually related to the direction of the area vector, okay? So just to give you an example, let's say that I have a wire that looks like this. Okay, and let's say I have current flowing through it here. So current flows in here and it flows out this way. So an electric current, which means there's charges that are flowing through here, right? If I come along and I look at a cross-sectional area of this wire down here, let's say, it might look something like that. But when I come up to this position, it might look something like this, okay? Those would be like cross-sectional cuts of it. If I wanted to define what the direction of the current density is at this point down here, it would point this way. But then when the wire points up like this, the current density would point that way. And again, it's a vector, basically. All right? And it points kind of in the direction of the wire, as defined by the cross-sectional area at that point of the wire. That's what we call current density. There's a way that we can connect current to current density, obviously through this equation here, but sometimes you're going to have a current density that's going to vary over an area, and in that case, we're going to define the current density by using something like this. Okay, so this is for way later in the class. This is for when we learn about Ampere's law, which will be in about 5 or 6 weeks, okay? So I'm writing it down now. Hopefully we've done enough of this type of stuff in this class at this point to understand that these two equations basically say exactly the same thing, okay? Except that the main difference is that I can write it, like writing the current density in the way that I have above, you can't really tell that it's a vector. It just looks like you take current and you divide by area. But if I write it like this, I can actually write it as a vector. So, okay. So don't let this scare you though. We'll get back to this later, and it's actually not that complicated. All right, so let's get back to our original question, which was how fast is the drift velocity? Because we're finally able to answer that question. We now have an equation that relates electric current to a bunch of other stuff and drift velocity, and that means we can calculate what the drift velocity is going to be. Okay. Before we go on to do that, does anyone have any questions about anything? Okay, if not, then we're going to try to solve this problem right here. All right, so it says a 12-gauge copper wire in a typical residential building has a cross-sectional area of 3.31 times, we'll just write this down, 10 to the negative 6 meters squared. So there's a cross-sectional area in this wire. In case you're wondering, the 12 gauge part of this is how copper wire is usually kind of, I don't know, sold or defined in, and yeah. So there's different types of gauges of wire, and different gauges of wire have different cross-sectional areas. You can go read more about that if you want to, but if you went and bought like a 6 gauge copper wire, it would have a different cross-sectional area. I can't remember if like I think as the gauge goes down, the cross-sectional area goes down. Could be wrong about that though. Anyway, so that's the cross-sectional area of our wire. So basically we have a wire. It's made of copper. And the cross-sectional area is A. It says it carries a constant current of 10 amps. So I'll just say that that's I. That's the current, 10.0 amps. We want to find the drift speed of electrons in the wire. We're going to assume that each copper atom contributes one free electron to the current. And we're also going to need to use the density of copper. So the density of copper, I'll use the symbol rho for that, is 8.92. I hate grams per centimeter cube. It's such an annoying... You have to convert both the grams and the centimeter cubed. Yeah, we'll just do it, I guess. So there's our density, 8.92 grams per centimeter cubed. And we want to find out, for the charges that are flowing inside of here, what is the drift velocity? And I know it says electrons. We're just going to treat them as positive charges. It's just a lot simpler than drawing the velocity backwards. So there we go. Our relationship that we're going to need to use to solve this was that the current is equal to the number of charges per unit volume multiplied by the charge on a single carrier, multiplied by the drift velocity, and then multiplied by the cross-sectional area. Let me make it so that that actually looks like a subscript. That's our relationship. Remember, I'm just going to rewrite here what these things represent, because I'm actually going to have you all calculate this. N represented the number of charge carriers, or just charges. I should say charge carriers, because there's a difference. Per unit volume. So it's a type of charge density, if you will. And I think everything else is self-explanatory. Q is going to be the charge on a single electron, so Q is basically just going to be equal to the electron charge, which is 1.6 times 10 to the negative 19 coulombs. That's the charge on a single electron. And I think that is enough information for you to figure this out. There is one other piece of information we're going to need, and I'm going to kind of like see if you all can figure out what that piece of information is before I ask you to calculate it. Okay, so in our equation, we know the current, we know the area, we also know the charge. So this is the thing that we actually have to think about what it is, the number of charges per unit volume. How can we do that? How can we figure out what N would be equal to in this case? Because if we can find it, then we can just directly calculate the drift velocity. How can we calculate the number of charge carriers per unit volume?
The number of, not the charges themselves, but the ones, like the atoms carrying the charges?
No. What you said first.
Okay.
Just the number of the charges.
The number.
So you have two pieces of information they're giving you, and there's going to be another piece of information you're going to have to go find yourself. But its atomic number. Or no, we already have one.
I guess you can find the amount of copper atoms within that area.
Or volume, right, Tal?
Yes, volume.
So yeah, so if we could figure out the number of copper atoms per unit volume, because we know that each atom contributes one electron. So if we knew the number of atoms, we would effectively know the number of charges per unit volume, right? Mm-hmm. So we really need the number of copper atoms per unit volume. How can we figure that out?
This looks
Using
like something like
moles
Avogadro.
Avogadro, yeah.
What'd you say,
Avogadro's
Dawes? Go ahead. What is it?
convert to moles and then use Avogadro's number to find atoms, and then you could convert your atoms into electrons.
Okay, we're definitely going to use Avogadro's number, that's for sure. What piece of information do we need to make those calculations, Dawes?
We had with density already, and we'd use our periodic table, which is we have our molar mass of
Molar mass. That's what we need, right? We need the molar mass, right? All right. So I'm going to use the symbol M to represent molar mass. I don't know if you use MM or what you use in your class. I'm just going to use big M for molar mass. And where do we find that? We find it on the periodic table, right? What does molar mass represent for those people that might not have taken chemistry?
The mass of 1 mole of that of atoms of that element.
Yeah, exactly. And since we know we know what 1 mole means. I don't know what this is. We just need to look up this tiny little number down here that's underneath copper. Oh no. That really didn't make it any better at all. I could read it a second ago. Okay, let's zoom back out. All right. This is a really bad periodic table. 63.546. That's the number we want, right? This number down here. So let's write that down. What is that unit in?
Grams per mole.
Yep, this is grams per mole. And the last thing we need is Avogadro's number, right?
Yep.
And what are the units for Avogadro's number?
Oh, it's like
number of
Atoms per mole, right?
Atoms per mole.
Yeah, atoms.
Atoms per mole, that's right. Okay, so we've got grams per volume, we've got grams per mole, and we've got atoms per mole. And really, we wanted to find number of atoms per mole because that's right. We ultimately want to basically convert all of these things into the number of copper atoms per unit volume, because that's going to be equivalent to the number of charge carriers per unit volume, because each atom contributes 1 electron. All right, does that strategy make sense? Do we have enough information here on the screen for you all to figure this out now?
Yep.
Okay, so what I want you all to do first is just focus on finding n. And of course, once you find n, you can calculate drift velocity if you want to, but all I want you to do first is just to calculate what n is, okay? So come up with a way, given the information on the screen here, to calculate n, and I want you to do it yourselves, and I'll give you a minute or so. So try to find n based on this information here. And if you want to write your answer as a bunch of symbols, you can do that. If you want to write it as a number, you can do that. Whatever you want to do. anyone have an answer yet?
I got something 8.45 times 10 to the 28th.
I got that too.
Yeah, that sounds right to me. So let's talk about in general how we would do this. So I would say that, did any of you come up with a symbolic way to calculate it based on based on this, this, and this? Can you help me to write down symbolic? What should I write down here to, what kind of calculation do we want to do?
So you want to take the molar mass
Okay.
and divide that by Avogadro's number.
I don't think
And
so.
then,
I would say Avogadro's
This needs
number
to be in the
is like
numerator. Atoms needs to be in the numerator, right?
mhm.
Yeah.
Oh, I just inversed everything at the end. That's what I did.
Okay, well that's going to be really confusing for me to write down. But
Yeah, okay.
but if you inverse it at the end, that means that it's in the numerator, right?
The way we always did this in chemistry is we'd write the expected. So we'd write atoms per mole on the outside, and then we just convert density all the way to what the ideal one that we. So like basically what I was saying is
Really, it's not. You don't want atoms per mole. You want atoms per volume,
atoms
right?
atoms per volume, right? So we'd write that on the side, and then we'd basically take density and we'd solve it all the way to our desired, or I should say units that we're looking for.
Yeah. We'll do that in terms of that stuff. I just wanted to see if someone could write it down in a simple form here.
It's just rho n over m.
Yeah, that's what I meant. Yeah, and then we'll write it out exactly like you said, Dawes. We'll do that for sure, just to make sure it's clear to everyone. All right, so it's rho n over m. What did you say, Cam? It's rho times Avogadro's number divided by the molar mass, right? Okay, let's see if this makes sense. Okay, so our goal is to get atoms per meter cubed. So what I'm going to do is we're going to say little n is going to be equal to, we can do it exactly as you said. We can basically say our answer over here needs to be in atoms per meter cubed. So we know meter cubed shows up in the denominator. To look through all these things, the density has meters cubed in the denominator, so we'll put that first. So we're going to say this is equal to 8.92 times 10 to the 6th grams over meters cubed. So I converted it into meters cubed because we need to have everything in SI units. The grams are okay though because it is going to cancel out with this. So let's do that next. Molar mass is this number of grams per mole, so let's put that next. So we know the grams needs to go on the bottom and the mole will go on the top. So we have 63.546 grams per 1 mole. And then we just need to go from moles to atoms. I guess I don't have enough room here. By putting in Avogadro's number here. So we want the atoms in the numerator. So 6.022 times 10 to the 23. Probably shouldn't have written that. Hey, how is it? There we go. All right, so 6 atoms on the top. And then we divide that by mole. And that should give us, we don't have enough room here for this one, what we want. And so you're always saying that if you calculate all of this, you end up getting something times 10 to the 28 atoms per mole, or atoms per meter cubed, right?
8.45.
Thank you. Okay, did that make sense to everyone? You don't have to take chemistry to take this class, so if you haven't taken chemistry and some of the things we're doing here seem like strange to you, feel free to ask a question. And if you don't feel comfortable asking a question in front of everyone, you can ask me after class. But at the end of the day, you're really just doing a conversion factor with all the information you're given. Okay, so you can see that this is the same as this, right? Because we have density multiplied by Avogadro's number, and then we're dividing by the molar mass. So all of that works too. Okay, now we're, I think, good to go to solve for the drift velocity. So we have drift velocity then is going to be equal to electric current, which is 10 amps. We need to divide by this number. Now, it's atoms per meter cubed, but it really also represents the number of charge carriers, right? So I'm just going to say that this is the number of charges per volume. Okay, because again, each atom contributes 1 charge. We need to multiply that by the charge on a single charge. So that's going to be 1.6 times 10 to the negative 19 coulombs. That's the charge on a single per charge. That way we can have it cancel out with the charges right here. And then we need to multiply it by the area. Everything has so many, every number here is so big. 3.31 times, I hope I can, let's see if we can fit this in here. 3.31 times 10 to the negative 6. All right, I'm just going to move this over. Do like that. All of that, meters cubed. Apologize that I'm writing upwards like this. It's hard to write in a straight line sometimes. So all of that stuff right there in the middle of this calculation.
Meters squared.
Oh yeah, it is meters squared. Thank you. That right there should be meters squared. Let me take this whole calculation and get it somewhere where we can actually see what we're doing. So that's what we're doing. That's the calculation. So what is that equal to?
Like 2.2 millimeters. A second.
Is that the answer? Do other people get the same answer?
I got, isn't it 0.22 millimeters per second?
Yeah, 0.22. That's right. Yeah, 0.22.
So yeah, so it ends up being about 2.23 times 10 to the negative 4. And if you look at all these units right here, the charges cancel. Amps, so 1 amp is equal to 1 coulomb per second. Let's just look at the units because I think it's important to do this stuff. So on the numerator, we basically have 1 coulomb per second. In the denominator, we have the charges are going to cancel. So you basically have coulombs over meter cubed times meter squared. So all of this, the coulombs cancel, one of the meters cancels. You're left with 1 meter in the denominator, which will move to the numerator because it's inverted. So this is going to give you units of meters per second, which is what you want. Okay, so it's 2.23 times 10 to the negative 4 meters per second. This is a very slow number, but using millimeters, as you guys were doing, I think is a good way to do this, because then if we can say the drift velocity is basically 0.22 millimeters per second, at basically about 1/5 of a millimeter per second. And if you think about how small a millimeter is, I mean, millimeters, extremely small, right? So for something to be only moving at 1/5 of a millimeter per second, well, that's extremely slow. So it turns out that the drift velocity is, I think, somewhat surprisingly, a very, very small number, especially when we're talking about charges that are very tiny. You know, we're talking about electrons that have, well, they're one of the smallest things in the universe. I mean, there's hardly anything in the universe is smaller than an electron. The only... What's smaller than an electron?
No, a quark?
Like, yeah, quarks and stuff.
Quarks are actually heavier than electrons.
Yeah, yeah.
Because they end up composing
like
the protons. And the protons are... What a proton is about 2,000 times as big as a single electron. Quark masses are weird, though, because you have their bound mass, their unbound mass. I don't know. You can't ever find quarks alone, so it's weird. Quarks are part of the universe, but they're really not part of our universe right now. They only exist as constituent parts of particles. So they're never free. As far as free particles go that can exist in the world, the only thing that I know of that's smaller than an electron is neutrinos and photons, things like that. Things that are little blips of energy that barely even matter in the grand scheme of things. As far as things that actually, physical matter is concerned, electrons are the smallest thing that we know about. So, the smallest thing that we know about moving at a speed this is slower than like an ant moves. Ants move faster than this. Millipedes move faster than this, right? I mean, this is an extremely, extremely slow speed.
But I was wondering, like,
Go ahead.
relative to the size of an electron, if we like scaled it up to like human size, how fast would that be? Like, if electrons were as big as us, like how fast would they be moving?
Well, you can notice that the mass of the electron never showed up in this equation. Right? So they'd be still moving the same speed.
Oh,
basically.
Wow. It's really slow.
Except you couldn't really, you couldn't really, to go back to what's really happening, if they were a lot bigger, they wouldn't really be able to fit through the thing. But if you expanded the whole thing, it would still be moving at the same rate. Yeah.
Oh, yeah.
It's a good question though, because the thing here is that like, what is the thing that's actually making these charges move? Well, it's the electric force, right?
Yeah.
And you have your electric field that's set up in your wire. Now, in order to know, based on the information given in this problem, in order to know how big the electric field itself is, we'd also need to know what the resistance of this wire is. Actually, we could calculate it. Maybe we could do that later if you want to. Because we know how long we don't really know how long the wire is, but we could pick a length. We know how fat the wire is, and we know that it's made of copper. So we actually could technically find, since we know the resistance, or we could calculate it, we could also find the potential difference that's applied to the wire, and we could then find the electric field in the wire. And then we could ask your question, and we could say, suppose that we scaled up the size of the electron given this size of an electric field. And the answer is that if we increase the size of the electrons, then they would move slower, based on that kind of idea, right? But it's a type of circular logic, because we already are given, this is basically the rate at which they're flowing, the amps, right? So we're already kind of knowing how fast they're flowing, basically. Anyway, but yeah, it's really, really slow, you know? Oh, it's 3:09 p.m. That's okay. We started a little late today. We probably should take a break, but just something to think about. These charges, they move very slowly, okay? So we're going to come back. We'll talk a little bit about that. Take a break now.